Hey guys, welcome back. Hope you all had a good weekend. Hope you guys are all staying safe. So we're back with day 3. We're going to be doing exponential growth and decay today. We're going to need a calculator for today's lesson, so go ahead and grab that. And again, just treat this like a normal class lesson. Just follow along, except you can pause. You can try the problems yourself, and have any questions, just send me an email. And on my last lesson, thank you to everyone that let me know I made a mistake. I think I said when we negated a function, it was a reflection over the y-axis. That is incorrect. It should be a reflection over the x-axis when you negate a function. So thanks to everyone that sent me an email telling me about that. I made a comment, or under the description in the video, I posted a fix for it. So again, thanks everyone that let me know. It'd also be great if you could leave like a comment or something, or just let people know on Google Classroom if you catch any mistakes. That'd be great. All right, share the knowledge. So guys, try this warm up. 2 pretty basic and important life skills: calculating the price of something after tax and the price of something after a discount. Alright, so hopefully you have tried these. I'm sure you can all do this, but it's the way you do it that I'm interested in. So if you are like my Algebra 1 kids, what they'd probably do is find the amount of tax there is. So they would take 8.9% of 65. So to get 8.9% of $65, well, we multiply this by 0.089. Right, if you forgot how to do that, you go from a percentage to a decimal. You're going to move the decimal place 2 spaces to the left. We're dividing by 100, and we get 65 times 0.089. Right, so that's the amount of the tax. And so if we add that to the original amount of the hoodie, we're going to get the final price. And I think that is something like $70.79 after rounding. And that's that. But another way to do this is, if you take a look at these 2 terms, there is a GCF of 65. So let's factor out that 65. We can also write this as 65 times 1 plus 0.089, which is, of course, 65 times 1.089. Right, and that's also going to be $70.79. So this is pretty cool. This 1.089 means that is an 8.9% increase to $65. Right? That one part, that's kind of like 100%. So we're including 100% of the cost originally, right? And then when we distribute 65 times 0.089, that's also going to count the percent increase, or the 8.9% tax. No, do not stop. All right. And we can apply a similar idea to a discount. I have $232 sneakers, and they're 15% off. To find the amount of the discount, we can multiply this by 0.15. So that's the amount of the discount. Discount amount. So the final price after the discount, well, we're going to subtract the discount from the original price of the sneakers. And what does that equal to? It's about 197.20, or maybe exactly 197.20. I don't know. But there we go. So we can also think about this as factoring out the 232 and just writing it as 1 minus 0.15, which is also 232 times 0.85. And I think it's equal 170 or 197.20. So if you have something that's decreasing value, well, we could multiply by something like 0.85. because when we multiply by 0.85, isn't that 85%? So if something's 15% off, we're paying for 85% of its value. So 85% of 232, well, that gives us the final price in one step. And this is how I want you guys to think as we do our exponential increase and decrease problems. All right, so there's some blank space here. We're going to come back and take some notes in a second. But take a look at 1 and 2 here, and I think you guys can give this a go. All right, so hopefully you tried these. And number 1 has a $450,000 house increasing in value by 4.2% each year. Find the value of the house after 5 years if it continues to grow at this rate. All right. So give me a sec. All right, so $450,000 house. Let's say I wanted to find the price after 1 year. Well, if it's growing by 4.2%, well, yes, I can multiply by 0.042, right, to get the percent increase, and then add that onto the original price, right? But based on what we did in the warm-up, I know this is the same thing as multiplying by 1.042, right? That 1 is going to account for the original 100% value of the house, and that 0.042, once I distribute or multiply, right, that's going to be the 4.2% increase. So to find the value of the house after 1 year, I just multiply by 1.042. To find the value of the house after 2 years, well, I can multiply by 1.042 twice, right, or squared. So to find the value of the house after 5 years, well, I'm going to multiply by 1.042 5 times. Right, so why don't we make a little table to see what's really happening here. I'm going to split it up into, let's say, t for time in years and the value of the house. So at time 0, the original value of the house is $450,000. After 1 year, right, if it's increasing by 4.2% each year, we're going to multiply by 1.042. And hold on, what is that equal to? Let me type this in. Times 1.042. That is 468,900. Multiply by 1.042 again. And that's going to be the price after 2 years. And that is 488,594. Any decimals? 0.80 after 2 years. Right? So you can see this is what we call exponential growth. Except we're not like doubling each time or tripling or decreasing by a half or multiplying by a third. Right? We're multiplying by 1.042, but that's still exponential growth. So when you see something increasing by a percent value each time, that's exponential growth because we're multiplying by 1.042 each time. All right, so of course we can just do that 5 times to get the value after 5 years. So in general, if I want to write this as a function, let's call the value f of t. Or even better, let's call it v of t, the value as a function of time. So the value of this house as a function of time is going to be, well, the original value, which is 450,000, times 1.042 to the t power, where t is the number of years. Right? If you think of it as what we did before, y equals a times b to the x, right? Isn't that a value our y-intercept here? 450,000. Our b value is our rate of growth, or a growth factor, 1.042, and x is t. So after 5 years, the value of the house after 5 years is going to be that. So I think I have this written down somewhere. If the number's wrong, I'm sorry. but I think it is 552,778.46. So how much did the value of the house increase over these years? By what percent did it increase? So we know it's increasing by 4.2% each year, but over the 5 years, how much did it increase by? So if you want to get the percent increase overall, what you can do is take the final price, 552,778.46, and divide it by the original price. And if we do that, I think we get 1.2284-ish. And I'm sorry we didn't answer the first part of the question. So this is by what percent did it increase? We actually didn't finish that. Okay, I'm sorry. Let's finish by what percent did it increase. So it started at 450,000, it ended at that. Another way to look at this is 450,000 times 1.2284, right? If you cross multiply, that is equal to 552,778.46. So this number here, that's what we multiplied by to go from the original value of the house to the final value of the house after 5 years. But this is not our percent increase, right? The percent increase is going to be just the decimal portion without the 1, right? Because that 1 includes the original value of the house, the 450,000. We don't want that 450,000 as part of our calculation. So we're going to do 1.2284 minus 1, and we're going to get 0.2284. So the percent it increased by is 22.84%. All right, cool? Another way to get the percent increase is, well, again, what did we multiply by overall? To go from 450,000 to this, right, we multiply by 1.042 to the 5th power. So if you did 1.042 to the 5th power, that is going to equal, or be approximately equal to 1.2284. And again, that's where we get our 22.84% increase. You can also do final price divided by original price, which of course also gets you by what we had to multiply by to get that increase, and we can use that value to get the percent increase. All right, hopefully that makes sense. But I did not answer the first part of the question. Hold on, redo. Okay. Which is, how much did the value of the house increase by? So take the final price, subtract the original price. Value of the house went up by over 100,000 in 5 years. It's pretty good investment. All right, but what if your house loses money? So if it loses money by 4.2% each year, well, we can do 450,000, 3. So if we're losing 4.2% each year, well, we can kind of do what we did in the warm-up, and we can multiply by that to get how much money we lose each year, and then subtract it and do that 5 times. That's a lot of work, though, right? So instead of multiplying this by 0.042, right, as a percentage, that's only going to give me the amount it decreases by each year. If I want the final price after the decrease, right, I can do 1 minus 0.042. What this is going to give me is 0.958. So let's think about this number. as a percent, that is 95.8%. So wouldn't you agree, if something loses 4.2% of its value, it is now worth 95.8% of what it was originally worth? Right? Maybe I should have picked an easier number like 5%. If something decreases in value by 5%, it's then going to be worth 95% of the original amount. So that's what we're doing here with 4.2%. Right? We're going to do 1, the original, 100% value, minus 4.2% or 0.042, then it's worth 95.8%. So to get the value of the house after each year, I can just multiply by 0.958. So if I want the value of the house after 2 years, I multiply by 0.958 squared. After 3 years cubed, after t number of years, it'll be just to the t power. So I guess I can call this v of t also. So the value of the house after t years is equal to that. If I want the value of the house after 5 years, that is going to be equal to, hold on, let me type this in my calculator. 450,000 times 0.958 to the fifth. And wow, it's a big decrease. That's going to be approximately equal to 363,112. And if we're talking about money, always round to the nearest cent, 0.55. Right, so how much did the value of the house decrease over these 5 years? Well, we know it increased by that amount. How much did it decrease by? Well, if you do 450,000 minus 363,000, whatever, you get, let's do it, 450,000 minus that. It decreased by 86,888.45. And that is not the same amount it increased by. So you can't just say, oh, if it's increasing by 4.2% over 5 years, it increases by this amount. So if it's decreasing by the same percentage, it's going to decrease by the same amount. It does not decrease by the same amount. They're quite different, in fact. Right? And the reason is, when we're increasing based on the previous price each year. So we're increasing on an increasing value. When we decrease each year, right, we're going to be decreasing based on a new lower value. So everything's different. You can't just assume percent increase is the same as the percent decrease. Right? So over the 5 years, what percent did it decrease by? Well, again, we can take the final value of the house and divide it by the original value. That's one way of doing it. So if you do that, 363,112.55 divide by 450,000, and let's see what that's equal to. $450,000. That's going to equal 0.8069-ish, approximately. So what percent did it decrease by? Did it decrease by 80.69%? No. Again, we have to subtract this from 100%. What this is saying is, after 5 years, it's worth 80% of what it was originally. So how much did it decrease by? What we have to do is 1 minus 0.8069, or 100% minus 80.69%. And so when we do that, what we get is 0.1931. In other words, it decreased by 19.31%. All right, this 0.8609 is not the percent decrease. It is the percent of the original price it was. It decreased by 19%, or about 20. All right. We can also take a look at this again. That is what we multiply by to go from the original price of the house to the final price of the house. So if you do 0.958, that's decreasing in value by 4.2%, 5 times. How much do we decrease by? Well, that is also 0.8069. And you do the same thing, you get the same answer. All right. So for exponential growth / decay, here are some formulas you can use, but hopefully those two problems we did kind of make some sense. But if you're looking at exponential growth, here is a formula for exponential growth. We can say the final amount, or the value of something, is going to equal its initial value, let's call that a sub 0, times, well, if we were growing at, I don't know, like 20%, we'd multiply by 1.2, or 1 plus 0.2. If we're growing by 5% each time, we'd multiply by 1 plus 0.05, etc. So what we're really doing is we're just adding our rate of growth onto 1. And after however many years, that's to the t power. So I don't know why I wrote a here. I think I actually like it better as a function. So let's say f of t is equal to that. So this a sub 0, that's going to be the initial value, or the initial amount. This r, that's going to be our rate of growth. In other words, that is our percent increase. But of course, you want to write that as a decimal. So whatever percent you're increasing by, divide that by 100. And altogether, this 1 plus r, that is what we're multiplying the initial value by each time, right? So something you multiply by something else, we call that a factor. So the entire thing, the 1 plus r, that is called the growth factor. And if something is decreasing in value, we're going to call that exponential decay. So if there's a percent decrease, if something is losing value by a percentage each year, we can write a function like f of t equals the original amount. So instead of adding the rate of growth, the only difference is we're going to subtract the rate of growth. For example, if something is losing 20% of its value each year, right, we're going to multiply by 1 minus 0.2. In other words, we're going to multiply by 0.8 because it's going to be worth 80% of what it was originally if it loses 20% of its value. So to get the final value, we can just multiply by 0.8. So in general, we're going to multiply by 1 minus what percent it's decreasing by raised to the t power. Right, so again, a sub 0, that is going to be the initial value. That 1 is really 100%. This r, that's going to be your rate of decay. And altogether, the 1 minus r, that is called the decay factor. All right, a lot of people mix up these two things. They're very different. One is the decay factor, what you're multiplying by. The other is the rate of decay. So for example, if your rate of decay were, let's say, I don't know. Let's do the same one. 20%. Your rate of decay would be 20% or 0.2. Your decay factor would be 0.8 or 80%. All right, cool. So moving on, we can answer some questions now. Let's skip 3 for now. Let's go down to number 4. Let's do 4 and 5 first. So an object's speed decreases by 5% for each minute that it's slowing down. Which of the following is closest to the percent that its speed will decrease over half an hour? Alright, something is decreasing in speed by 5% each minute. How much will it decrease in speed? By what percent? In half an hour. Alright, so let's say the original speed is whatever. Some speed, let's call it a sub 0 for the original speed. Right, if it's decreasing by 5%, we're going to multiply that by 1 minus 0.05. Right, 0.05 is the 5%. In other words, the original speed is going to be 95% of what it was after 1 minute. So how much speed is it going to lose after half an hour? Well, after 1 hour, it loses 95% of its speed. After 2 hours, it's going to lose 95% of its speed twice, or multiplied by 0.95 twice. I don't like a sub 0 anymore. Hold on. Original speed. Right, so after 30 minutes, we're going to multiply by 0.95 30 times. So if you do that, what are we multiplying the original speed by? Well, 0.95 to the 30th power is equal to, let's take a look, equal to 0.214639-ish. So you might be thinking, okay, good, 21%. There we go, that's our answer, 21%. No, it did not lose 21% of its speed. Think about it, if you're losing 5% 30 times, that's not going to add up to 20%. What's really happening is, well, we're multiplying the original speed by 0.95 to the 30th, which was 0.2146. I'm just going to round to 0.21. So in other words, we have 21% of the original speed. So how much speed did we lose? Well, we have to do 1 minus this quantity. 1 minus 0.214639. So that is whatever it is. But that's going to be approximately 79%. All right, think about that for a second. Does that make sense? We lost 79% of our speed. We have 21% of the speed remaining. We lost 79% of the speed. So that's the percent decrease over the 30 minutes. All right. Next, number 5. Population of wolves in a county is represented by this equation, where T is the number of years since 1998. So what's the initial population in 1998? Well, if you remember the formula, that is our y-intercept. That's the original amount, the initial value. So the initial number of wolves here is 80. I mean, you could also just plug in a 0 for t, right, at time 0. What do we get? That's equal to 1, so it's just 80. Right, is the population of wolves increasing or decreasing? How can you tell? Just by looking at the equation, and by what percent is it decreasing? So our original population of 80, we're multiplying it by 0.974. So this here, that is our growth factor. What would be the growth factor if it were more than 1? So it's less than 1, so that's going to make it a decay factor. Right? If we're multiplying something by a number less than 1, it's going to be decreasing. So we know it's decaying. So number of wolves, it's getting less and less. In fact, that as a percentage is 97.4%. Right? So if you have 97.4% of 80 wolves, you're going to have less wolves. So how do you know by looking at the function? I know because my factor is less than 1. So by what percent is it decreasing? Again, I don't know why I erased that, but it's not decreasing by 97.4%. It's decreasing by 1 minus 0.974. And that's equal to 0.026. So the rate of decrease is 2.6%. Right? Wouldn't it make sense that we're losing 97% of the wolves each year? We're losing 2.6% because we have 97% of them left after each year. Right, so how many wolves are there in the county in 2010? This is just simply plugging in for T. So don't plug in 2010. Make sure you read the question. What is the initial population in 1998? That was 80. So in 2010, that's not going to be 2010 years after 1998. T was years since 1998. So 2010 is 12 years after. And just plugging that into the equation, 80 times 0.974 to the 12th power will be, I don't know, approximately whatever. I'll let you guys do the calculation, but there you go. All right, round to the nearest wolf. And for 3, so sometimes the percent rate of increase or decrease or the growth factor or decay factor isn't written out nicely, and you need to do a little bit of work to find it. So let's take a look at a couple of these. For this first one, f of t, we can clearly see that we're increasing by 4%, right? That is 1.04, so that's a 4% increase, right? As a decimal, it's 104%, so we're increasing by 4%. You can also take a look at the formula. That's a sub 0 times 1 plus r to the t, right? In this case, r is positive, so that's our rate of increase. And what's the growth or decay factor? If we have a 4% increase, our growth factor is 1.04. That is what we're multiplying by. Growth factor and 4% increase or 4% rate of growth. All right, JFT. This is just written weird with a negative here. So if you follow order of operations, we can rewrite this as 6.3 times 0.729 to the negative first power times t, right, to the negative t power. And so to get the actual rate of increase or decrease, I need to figure out what 0.729 to the negative first is. 0.729 to the negative first power is 1.37174. I'm sure there's more decimals after that. Yeah, but approximately that to the t power, 6.3. So we're originally starting with 6.3 whatever, and even though this number here was less than 1, because of that negative, that's really 1 over this number, so this is actually a percent increase. And so this one is increasing by 37.17%. All right, I should tell you guys what to round to, I'm sorry, but yeah. It's a 37.17% increase, which means our growth factor is 1.37174. All right, this one again, nice and easy, 1.021, that's 1 plus 0.021. This here is 2.1%. That is our percent increase, our rate of growth. Our growth factor is 1.021. All right. This here number in the parentheses is going to be less than 1, so it's a percent decrease. What are we decreasing by? We're decreasing by 0.03 or 3%. So this is a 3% decrease, or rate of exponential decay is 3%. The decay factor, sorry, I was thinking of the name of it. The decay factor, that is equal to 0.97. All right. Next here, again, before we can get the actual percent increase or decrease, we need to clean this up. And so I'm going to do 0.56 to the 2.5th power. That is approximately 0.2347 to the t power. So we're decreasing by 76 point, what is that, 53% ish. But it also means our decay factor is 0.2347. All right. In other words, we're multiplying by, again, 23.47. We're taking 23.47% of the previous value. So that's what we're multiplying by, the factor, and that means we're decreasing by that amount. Right, and this last one, why did I put an E here? We'll save this for later. We don't know what E is yet, so I don't want to bother you with that. So that's that. If you have any questions, just send me an email or send me a message on Google Classroom. You don't have to make it a private comment. If you have a question, I'm sure a lot of other people have questions as well. So if you want, you can post it as a public comment or private, I don't care. And I'll get back to you guys. All right, so see you guys soon. Bye-bye.